King Authentication. It remains current and has only minor updates. Chapter 7. The Attacking Session Management. It has been updated to cover new tools for automatically testing the quality of randomness. Also contains new material on attacking encrypted tokens, including practical techniques for token tampering without knowing either the cryptographic algorithm or their encryption key being used. Chapter 8. The Attacking Access Controls, and now covers access control vulnerabilities arising from direct access to server-side methods, and from platform misconfiguration where rules based on HTTP methods are used to control access. It also describes some new tools and techniques you can use to partially automate the frequently onerous task of testing access controls. The material in chapters 9 and 10 has been reorganized to create more manageable chapters and a more logical arrangement of topics. Chapter 9, Attacking. Data stores focuses on SQL injection and similar attacks against other data store technologies. As SQL injection vulnerabilities have become more widely understood and addressed, this material now focuses more on practical situations where SQL injection is still found. There are also minor updates through out to refer ECT, current technologies and attack methods. A new section on using automated tools for exploiting SQL injection vulnerabilities is included. The material on LDAP injection has been largely rewritten to include more detailed introduction XI coverage of specify C technologies, Microsoft Active Directory, and OpenLDAP, as well as new techniques for exploiting common vulnerabilities. This chapter also now covers attacks against NoSQL. Chapter 10, Attacking Backend Components, covers the other types of server-side injection vulnerabilities that were previously included in Chapter 9. New sections cover XML external entity injection and injection into backend. HTTP requests, including HTTP parameter injection for pollution and injection into URL rewriting schemes. Chapter 11, Attacking Application Logic, includes more real-world examples of common logic FLAWS in input validation functions. With the increased usage of encryption to protect application data at rest, we also include an example of how to identify and exploit encryption oracles to decrypt encrypted data. The topic of attacks against other application users, previously covered in Chapter 12, has been split into two chapters because this material was becoming unmanageably large. Chapter 12, Attacking Users, Cross-Site Scripting, focuses solely on XSS. This material has been extensively updated in various areas. The sections on bypassing defensive file filters to introduce script code have been completely rewritten to cover new techniques and technologies, including various little-known methods for executing script code on current browsers. There is also much more detailed coverage of methods for obfuscating script code to bypass common input file filters. The chapter includes several new examples of real-world XSS attacks. A new section on delivering working XSS exploits in challenging conditions covers escalating an attack across application pages, exploiting XSS via cookies and the refer header, and exploiting XSS in non-standard request and response content such as XML. There is a detailed examination of browsers' built-in XSS file filters and how these can be circumvented to deliver exploits. New sections discuss specify C techniques for exploiting XSS in webmail applications and in uploaded files. Finally, there are various updates to the defensive measures that can be used to prevent XSS attacks. The new Chapter 13, Attacking Users, Other Techniques, unites the remainder of this huge area. The topic of cross-site request forgery has been updated to include CSRF attacks against the login function, common defects in anti-CSRF defenses, UI redress attacks, and common defects in frame-busting defenses. A new section on cross-domain data capture includes techniques for stealing data by injecting text containing non-scripting HTML and CSS and various techniques for cross-domain data capture using JavaScript and E4X. A new section examines the same origin policy in more detail, including its implementation in different browser extension technologies, the changes brought by HTML5, and ways of crossing domains via proxy service applications. There are new sections on client-side cookie injection, SQL injection, and HTTP parameter pollution. The section on client-side privacy attacks has been expanded to include storage mechanisms provided by browser extension technologies and HTML5. Finally, a new section has been added drawing together general attacks against XXI introduction. Web users that do not depend on vulnerabilities in any particular application. These attacks can be delivered by any malicious or compromised website or by an attacker who is suitably positioned on the network. Chapter 14, Automating Customized Attacks, has been expanded to cover common barriers to automation and how to circumvent them. Many applications employ defensive session handling mechanisms that terminate sessions, use ephemeral anti-CSRF tokens, or use multi-stage processes to update application state. Some new tools are described for handling these mechanisms, which let you continue using automated testing techniques. A new section examines capture controls and some common vulnerabilities that can often be exploited to circumvent them. Chapter 15, Exploiting Information Disclosure, contains new sections about XSS in error messages and exploiting decryption oracles. Chapter 16, Attacking Native Compiled Applications, has not been updated. Chapter 17, Attacking Application Architecture, has a new section about Vulnerabilities that arise in cloud-based architectures, and updated examples of exploiting architecture weaknesses. Chapter 18, Attacking the Application Server, contains several new examples of interesting vulnerabilities in application servers and platforms, including Jetty. The JMX Management Console, ASP.NET, Apple iDisk Server, Ruby WE Brick Web Server, and Java Web Server. It also has a new section on practical approaches to circumventing web application firewalls. Chapter 19, Finding Vulnerabilities in Source Code, has not been updated. Chapter 20, A Web Application Hacker's Toolkit, has been updated with details on the latest features of proxy-based tool suites. It contains new sections on how to proxy the traffic sea of non-proxy-aware clients and how to eliminate SSL errors in browsers and other clients caused by the use of an intercepting proxy. This chapter contains a detailed description of the workflow that is typically employed when you test using a proxy-based tool suite. It also has a new discussion about current web vulnerability scanners and the optimal approaches to using these in different situations. Chapter 21, A Web Application Hacker's Methodology, has been updated to refer ECT, the new methodology steps described throughout the book. Tools you will need. This book is strongly geared toward hands-on techniques you can use to attack web applications. After reading the book, you will understand the specified CS of each individual task, what it involves technically, and why it helps you detect and exploit vulnerabilities. The book is emphatically not about downloading a tool, pointing it at a target application, and believing what the tool's output tells you about the state of the application's security. Introduction XC. That said, you will find several tools useful and sometimes indispensable when performing the tasks and techniques we describe. All of these are available on the internet. We recommend that you download and experiment with each tool as you read about it. What's on the website? The companion website for this book app//mdcec.net, which you can also link to from www.wiley.com to go a web hacker 2e, contains several resources that you will find useful in the course of mastering the techniques we describe and using them to attack actual applications. In particular, the website contains access to the following: source code for some of the scripts we present in the book, a list of current links to all the tools and other resources discussed in the book, a handy checklist of the tasks involved in attacking a typical application, answers to the questions posed at the end of each chapter, hundreds of interactive vulnerability labs that are used in examples throughout this book and that are available on a subscription basis to help you develop and refine your skills. Bring it on. Web application security remains a fun and thriving subject. We enjoyed it in this book as much as we continue to enjoy hacking into web applications on a daily basis. We hope that you will also take pleasure from learning about the different techniques we describe and how you can defend against them. Before going any further, we should mention an important caveat. In most countries, attacking computer systems without the owner's permission is against the law. The majority of the techniques we describe are illegal if carried out without consent. The authors are professional penetration testers who routinely attack web applications on behalf of clients to help them improve their security. In recent years, numerous security professionals and others have acquired criminal records and ended their careers by experimenting on or actively attack in computer systems without permission. We urge you to use the information contained in this book only for lawful purposes. Chapter 1. Web application in security. There is no doubt that web application security is a current and newsworthy subject. For all concerned, the stakes are high, for businesses that derive increase in revenue from internet commerce, for users who trust web applications with sensitive information, and for criminals who can make big money by stealing payment details or compromising bank accounts. Reputation plays a critical role. Few people want to do business with an insecure website, so few organizations want to disclose details about their own security vulnerabilities or breaches. Hence, it is not a trivial task to obtain reliable information about the state of web application security today. This chapter takes a brief look at how web applications have evolved and the many benefits they provide. We present some metrics about vulnerabilities in current web applications, drawn from the author's direct experience, demonstrating that the majority of applications are far from secure. We describe the core security problem facing web applications, that users can supply arbitrary input, and the various factors that contribute to their weak security posture. Finally, we describe the latest trends in web application security and how these may be expected to develop in the near future. 1. 2. Chapter 1, Web Application in Security. The evolution of web applications. In the early days of the internet, the World Wide Web consisted only of websites. These were essentially information repositories containing static documents. Web browsers were invented as a means of retrieving and displaying those documents, as shown in Figure 1.1. The FLO of interesting information was one way, from server to browser. Most sites did not authenticate users because there was no need to. Each user was treated in the same way and was presented with the same information. Any security threats arising from hosting a website were related largely to vulnerabilities in web server software, of which there were many. If an attacker compromised a web server, he usually would not gain access to any sensitive information because the information held on the server was already open to public view. Rather, an attacker typically would modify the files on the server to deface the website's contents, or use the server's storage and bandwidth to distribute WARs. Figure 1.1, a traditional website containing static information. Today, the World Wide Web is almost unrecognizable from its earlier form. The majority of sites on the web are in fact applications, see Figure 1.2. They are highly functional and rely on two-way flow of information between the server and browser. They support registration and login, financial transactions. Chapter 1 Web Application in Security. 3. Search and the authoring of content by users. The content presented to users is generated dynamically on the FLY and is often tailored to each specify C user. Much of the information processed is private and highly sensitive. Security, therefore, is a big issue. No one wants to use a web application if he believes his information will be disclosed to unauthorized parties. Figure 1.2, a typical web application. Web applications bring with them new and significant security threats. Each application is different and may contain unique vulnerabilities. Most applications are developed in-house, many by developers who have only a partial understanding of the security problems that may arise in the code they are producing. To deliver their core functionality, web applications normally require connectivity to internal computer systems that contain highly sensitive data and that can perform powerful business functions. 15 years ago, if you wanted to make a funds transfer, you visited your bank and the teller performed the transfer for you. Today, you can visit a web application and perform the transfer yourself. An attacker who compromises a web application may be able to steal personal information, carry out financial fraud, and perform malicious actions against other users. 4. Chapter 1 Web Application in Security. Common web application functions. Web applications have been created to perform practically every useful function you could possibly implement online. Here are some web application functions that have risen to prominence in recent years. Shopping, Amazon. Social networking, Facebook. Banking, Citibank. Web search for Google. Auctions, eBay. Gambling, Betfair. Weblogs, Blogger. Webmail, Gmail. Interactive information, Wikipedia. Applications that are accessed using a computer browser increasingly overlap with mobile applications that are accessed using a smartphone or tablet. Most mobile applications employ either a browser or a customized client that uses HTTP-based APIs to communicate with the server. Application functions and data typically are shared between the various interfaces that the application exposes to different user platforms. In addition to the public internet, web applications have been widely adopted inside organizations to support key business functions. Many of these provide access to highly sensitive data and functionality. HR applications allowing users to access payroll information, give and receive performance feedback, and manage recruitment and disciplinary procedures. Administrative interfaces to key infrastructure such as web and mail. Servers, user workstations, and virtual machine administration. Collaboration software used for sharing documents, managing work, LO and projects, and tracking issues. These types of functionality often involve critical security and governance issues, and organizations often rely completely on the controls built into their web applications. Business applications such as enterprise resource planning, ERP, software, which previously were accessed using a proprietary thick client application, can now be accessed using a web browser. Chapter 1 Web Application in Security. 5. Software services such as email, which originally required a separate email client, can now be accessed via web interfaces such as Outlook Web Access. Traditional desktop Office CE applications, such as word processors and spread sheets, have been migrated to web applications through services such as Google Apps and Microsoft Office CE Live. In all these examples, what are perceived as internal applications are increasingly being hosted externally as organizations move to outside service providers to cut costs. In these so-called cloud solutions, business-critical functionality and data are opened to a wider range of potential attackers, and organizations are increasingly reliant on the integrity of security defenses that are outside of their control. The time is fast approaching when the only client software that most computer users will need is a web browser. A diverse range of functions will have been implemented using a shared set of protocols and technologies, and in so doing will have inherited a distinctive range of common security vulnerabilities. Benefits of web applications. It is not difficult to see why web applications have enjoyed such a dramatic rise to prominence. Several technical factors have worked alongside the obvious commercial incentives to drive the revolution that has occurred in how we use the internet. HTTP, the core communications protocol used to access the World Wide Web, is lightweight and connectionless. This provides resilience in the event of communication errors and avoids the need for the server to hold open a network connection to every user, as was the case in many legacy client or server applications. HTTP can also be proxied and tunneled over other protocols, allowing for secure communication in any network configuration. Every web user already has a browser installed on his computer and mobile device. Web applications deploy their user interface dynamically to the browser, avoiding the need to distribute and manage separate client software, as was the case with pre-web applications. Changes to the interface need to be implemented only once on the server and take effect immediately. Today's browsers are highly functional, enabling rich and satisfying user interfaces to be built. Web interfaces use standard navigational and 6. Chapter 1 Web Application in Security. Input controls that are immediately familiar to users, avoiding the need to learn how each individual application functions. Client-side scripting enables applications to push part of their processing to the client side and Browser's capabilities can be extended in arbitrary ways using browser extension technologies where necessary. The core technologies and languages used to develop web applications are relatively simple. A wide range of platforms and development tools are available to facilitate the development of powerful applications by relative beginners, and a large quantity of open source code and other resources is available for incorporation into custom-built applications. Web application security. As with any new class of technology, web applications have brought with them a new range of security vulnerabilities. The set of most commonly encountered defects has evolved somewhat over time. New attacks have been conceived that were not considered when existing applications were developed. Some problems have become less prevalent as awareness of them has increased. New technologies have been developed that have introduced new possibilities for exploitation. Some categories of FLAWS have largely gone away as the result of changes made to web browser software. The most serious attacks against web applications are those that expose sensitive data or gain unrestricted access to the back-end systems on which the application is running. High-profile compromises of this kind continue to occur frequently. For many organizations, however, any attack that causes system downtime is a critical event. Application-level denial of service attacks can be used to achieve the same results as traditional resource exhaustion attacks against infrastructure. However, they are often used with more subtle techniques and objectives. They may be used to disrupt a particular user or service to gain a competitive edge against peers in the realms of financial trading, gaming, online bidding, and ticket reservations. Throughout this evolution, compromises of prominent web applications have remained in the news. There is no sense that a corner has been turned in that these security problems are on the wane. By some measure, web application security is today the most significant battleground between attackers and those with computer resources and data to defend, and it is likely to remain so for the foreseeable future. Chapter 1 Web Application in Security. 7. This site is secure. There is a widespread awareness that security is an issue for web applications. Consult the FAQ page of a typical application, and you will be reassured that it is in fact secure. Most applications state that they are secure because they use SSL. For example, this site is absolutely secure. It has been designed to use 128-bit secure socket layer SSL technology to prevent unauthorized users from viewing any of your information. You may use this site with peace of mind that your data is safe with us. Users are often urged to verify the site's certificate, admire the advanced cryptographic protocols in use, and on this basis, trust it with their personal information. Increasingly, organizations also cite their compliance with payment card industry (PCI) standards to reassure users that they are secure. For example, we take security very seriously. Our website is scanned daily to ensure that we remain PCI compliant and safe from hackers. You can see the date of the latest scan on the logo below, and you are guaranteed that our website is safe to use. In fact, the majority of web applications are insecure, despite the widespread usage of SSL technology and the adoption of regular PCI scanning. The authors of this book have tested hundreds of web applications in recent years. Figure 1.3 shows what percentage of applications tested during 2007 and 2011 were found to be affected by some common categories of vulnerability. Broken authentication, 62%. This category of vulnerability passes various defects within the application's login mechanism, which may enable an attacker to guess weak passwords, launch a brute force attack, or bypass the login. Broken access controls, 71%. This involves cases where the application fails to properly protect access to its data and functionality, potentially enabling an attacker to view other users' sensitive data held on the server or carry out privileged actions. SQL injection, 32%. This vulnerability enables an attacker to submit crafted input to interfere with the application's interaction with backend databases. An attacker may be able to retrieve arbitrary data from the application, interfere with its logic, or execute commands on the database server itself. 8. Chapter 1 Web Application in Security. Cross-site scripting, 94%. This vulnerability enables an attacker to target other users of the application, potentially gaining access to their data, performing unauthorized actions on their behalf, or carrying out other attacks against them. Information leakage, 78%. This involves cases where an application divulges sensitive information that is of use to an attacker in developing an assault against the application through defective error handling or other behavior. Cross-site request forgery, 92%. This FL or means that application users can be induced to perform unintended actions on the application within their user context and privilege level. The vulnerability allows a malicious website visited by the victim user to interact with the application to perform actions that the user did not intend. Broken authentication. Broken access controls. SQL injection. Cross-site scripting. Information leakage. Cross-site request forgery. 62%. 32%. 71%. 94%. 78%. 92%. 0%, 10%, 20%, 30%, 40%, 50%, 60%, 70%, 80%, 90%, 100%. Incidents in recently tested applications. Figure 1.3. The incidence of some common web application vulnerabilities in applications recently tested by the authors, based on a sample of more than 100. SSL is an excellent technology that protects the confidentiality and integrity of data in transit between the user's browser and the web server. It helps defend against eavesdroppers, and it can provide assurance to the user of the identity of the web server he is dealing with. But it does not stop attacks that directly target the server or client components of an application, as most successful attacks do. Specify cowly, it does not prevent any of the vulnerabilities just listed, or many others that can render an application critically exposed to attack. Regardless of whether they use SSL, most web applications still contain security FLAWS. Chapter 1 Web Application in Security. 9. The core security problem, users can submit arbitrary input. As with most distributed applications, web applications face a fundamental problem they must address to be secure. Because the client is outside of the application's control, users can submit arbitrary input to the server-side appli. Cation. The application must assume that all input is potentially malicious. Therefore, it must take steps to ensure that attackers cannot use crafted input to compromise the application by interfering with its logic and behavior, thus gaining unauthorized access to its data and functionality. This core problem manifests itself in various ways. Users can interfere with any piece of data transmitted between the client and the server, including request parameters, cookies, and HTTP headers. Any security controls implemented on the client side, such as input validation checks, can be easily circumvented. Users can send requests in any sequence and can submit parameters at a different stage than the application expects, more than once, or not at all. Any assumption developers make about how users will interact with the application may be violated. Users are not restricted to using only a web browser to access the application. Numerous widely available tools operate alongside, or independently of, a browser to help attack web applications. These tools can make requests that no browser would ordinarily make, and can generate huge numbers of requests quickly to find and exploit problems. The majority of attacks against web applications involve sending input to the server that is crafted to cause some event that was not expected or desired by the application's designer. Here are some examples of submitting crafted input to achieve this objective. Changing the price of a product transmitted in a hidden HTML form file ELD. To fraudulently purchase the product for a cheaper amount. Modifying a session token transmitted in an HTTP cookie to hijack the session of another authenticated user. Removing certain parameters that normally are submitted to exploit a logic FL or in the application's processing. Altering some input that will be processed by a backend database to inject a malicious database query and access sensitive data. Needless to say, SSL does nothing to stop an attacker from submitting crafted input to the server. If the application uses SSL, this simply means that other users on the network cannot view or modify the attacker's data in transit. Because 10. Chapter 1 Web Application in Security. The attacker controls her end of the SSL tunnel. She can send anything she likes to the server through this tunnel. If any of the previously mentioned attacks are successful, the application is emphatically vulnerable, regardless of what its FAQ may tell you. Key problem factors. The core security problem faced by web applications arises in any situation where an application must accept and process untrusted data that may be malicious. However, in the case of web applications, several factors have combined to exacerbate the problem and explain why so many web applications on the internet today do such a poor job of addressing it. Underdeveloped security awareness. Although awareness of web application security issues has grown in recent years, it remains less well developed than in long-established areas such as networks and operating systems. Although most people working in IT security have a reasonable grasp of the essentials of securing networks and hardening hosts, widespread confusion and misconception still exist about many of the core concepts involved in web application security. A web application developer's work increasingly involves weaving together tens, or even hundreds, of third-party packages, all designed to abstract the developer away from the underlying technologies. It is common to meet experienced web application developers who make major assumptions about the security provided by the programming framework, and to whom an explanation of many basic types of FLAWS comes as a revelation. Custom development. Most web applications are developed in-house by an organization's own staff or third-party contractors. Even where an application employs well-established components, these are typically customized or bolted together using new code. In this situation, every application is different and may contain its own unique defects. This stands in contrast to a typical infrastructure deployment in which an organization can purchase a best-of-breed product and install it in line with industry-standard guidelines. Deceptive simplicity. With today's web application platforms and development tools, it is possible for a novice programmer to create a powerful application from scratch in a short period of time. But there is a huge difference between producing code that is Chapter 1 Web Application in Security. 11. Functional and code that is secure. Many web applications are created by well-meaning individuals who simply lack the knowledge and experience to identify where security problems may arise. A prominent trend in recent years has been the use of application frameworks that provide ready-made code components to handle numerous common areas of functionality, such as authentication, page templates, message boards, and integration with common backend infrastructure components. Examples of these frameworks include Liferay and AppFuse. These products make it quick and easy to create working applications without requiring a technical understanding of how the applications work or the potential risks they may contain. This also means many companies use the same frameworks. Thus, when a vulnerability is discovered, it affects many unrelated applications. Rapidly evolving threat profiler. Research into web application attacks and defenses continues to be a thriving area in which new concepts and threats are conceived at a faster rate than is now the case for older technologies. Particularly on the client side, it is common for the accepted defenses against a particular attack to be undermined by research that demonstrates a new attack technique. A development team that begins a project with a complete knowledge of current threats may have lost this status by the time the application is completed and deployed. Resource and time constraints. Most web application development projects are subject to strict constraints on time and resources arising from the economics of in-house, one-off development. In most organizations, it is often infeasible to employ dedicated security expertise in the design or development teams. And due to project slippage, security testing by specialists is often left until very late in the project's life cycle. In the balancing of competing priorities, the need to produce a stable and functional application by a deadline normally overrides less tangible security considerations. A typical small organization may be willing to pay for only a few man-days of consulting time to evaluate a new application. A quick pen iteration test will often find the low-hanging fruit, but it may miss more subtle vulnerabilities that require time and patience to identify. Overextended technologies. Many of the core technologies employed in web applications began life when the landscape of the World Wide Web was very different. They have since been pushed far beyond the purposes for which they were originally conceived, such as the use of JavaScript as a means of data transmission in many Ajax-based 12. Chapter 1 Web Application in Security Applications. As the expectations placed on web application functionality have rapidly evolved, the technologies used to implement this functionality have lagged behind the curve, with old technologies stretched and adapted to meet new requirements. Unsurprisingly, this has led to security vulnerabilities as unforeseen side effects emerge. Increasing demands on functionality. Applications are designed primarily with functionality and usability in mind. One static user profiles now contains social networking features, allowing uploading of pictures and wiki-style editing of pages. A few years ago, an application designer may have been content with implementing a username and password challenge to create the login functionality. Modern sites may include password recovery, username recovery, password hints, and an option to remember the username and password on future visits. Such a site would undoubtedly be promoted as having numerous security features, yet each one is really a self-service feature adding to the site's attack surface. The new security perimeter. Before the rise of web applications, organizations' efforts to secure themselves against external attack were largely focused on the network perimeter. Defending this perimeter entailed hardening and patching the services it needed to expose and firewalling access to others. Web applications have changed all this. For an application to be accessible by its users, the perimeter firewall must allow inbound connections to the server over HTTP or HTTPS. And for the application to function, the server must be allowed to connect to supporting backend systems, such as databases, mainframes, and financial and logistical systems. These systems often lie at the core of the organization's operations and reside behind several layers of network-level defenses. If a vulnerability exists within a web application, an attacker on the public internet may be able to compromise the organization's core backend systems solely by submitting crafted data from his web browser. This data sails past all the organization's network defenses in the same way as does ordinary, benign traffic to the web application. The effect of widespread deployment of web applications is that the security perimeter of a typical organization has moved. Part of that perimeter is still embodied in firewalls and bastion hosts, but a significant part of it is now occupied by the organization's web applications. Because of the manifold ways in which web applications receive user input and pass this to sensitive backend systems, they are the potential gateways for a wide range of attacks, and defenses against these attacks must be implemented within the applications themselves. A single Chapter 1 Web Application in Security 13. Line of defective code in a single web application can render an organization's internal systems vulnerable. Furthermore, with the rise of mashup applications, third-party widgets, and other techniques for cross-domain integration, the server-side security perimeter frequently extends well beyond the organization itself. Implicit trust is placed in the services of external applications and services. The statistics described previously of the incidence of vulnerabilities within this new security perimeter should give every organization pause for thought. Note: for an attacker targeting an organization, gaining access to the network or executing arbitrary commands on servers may not be what he wants to achieve. Often, and perhaps typically, what an attacker really wants is to perform some application-level action, such as stealing personal information, transferring funds, or making cheap purchases. And the relocation of the security perimeter to the application layer may greatly assist an attacker in achieving these objectives. For example, suppose that an attacker wants to hack into a bank's systems and steal money from users' accounts. In the past, before the bank deployed a web application, the attacker might have needed to find a vulnerability in a publicly reachable service, exploit this to gain a toehold on the bank's DMZ, penetrate the firewall restricting access to its internal systems, map the network to find the mainframe computer, decipher the arcane protocol used to access it, and guess some credentials to log in. However, if the bank now deploys a vulnerable web application, the attacker may be able to achieve the same outcome simply by modifying an account number in a hidden ELD of an HTML form. A second way in which web applications have moved the security perimeter arises from the threats that users themselves face when they access a vulnerable application. A malicious attacker can leverage a benign but vulnerable web Application to attack any user who visits it. If that user is located on an internal corporate network, the attacker may harness the user's browser to launch an attack against the local network from the user's trusted position. Without any cooperation from the user, the attacker may be able to carry out any action that the user could perform if she were herself malicious. With the proliferation of browser extension technologies and plugins, the extent of the client-side attack surface has increased considerably. Network administrators are familiar with the idea of preventing their users from visiting malicious websites, and end users themselves are gradually becoming more aware of this threat. But the nature of web application vulnerabilities means that a vulnerable application may present no less of a threat to its users and their organization than a website that is overtly malicious. Correspondingly, the new security perimeter imposes a duty of care on all application owners to protect their users from attacks against them delivered via the application. 14. Chapter 1 Web Application in Security. A further way in which the security perimeter has partly moved to the client side is through the widespread use of email as an extended authentication mechanism. A huge number of today's applications contain forgotten password functions that allow an attacker to generate an account recovery email to any registered address without requiring any other user-specified information. This allows an attacker who compromises a user's webmail account to easily escalate the attack and compromise the victim's accounts on most of the web applications for which the victim is registered. The future of web application security. Over a decade after their widespread adoption, web applications on the internet today are still rife with vulnerabilities. Understanding of the security threats facing web applications and effective ways of addressing these are still developed within the industry. There is currently little indication that the problem factors described in this chapter will disappear in the near future. That said, the details of the web application security landscape are not static. Even though old and well-understood vulnerabilities, such as SQL injection, continue to appear, their prevalence is gradually diminishing. Furthermore, the instances that remain are becoming more difficult to find and exploit. New research in these areas is generally focused on developing advanced techniques for attacking more subtle manifestations of vulnerabilities that a few years ago could be easily detected and exploited using only a browser. A second prominent trend has been a gradual shift in attention from attacks against the server side of the application to those that target application users. The latter kind of attack still leave rich defects within the application itself, but it generally involves some kind of interaction with another user to compromise that user's dealings with the vulnerable application. This is a trend that has been replicated in other areas of software security. As awareness of security threats matures, FLAWS in the server side are the FIRST to be well understood and addressed, leaving the client side as a key battleground as the learning process continues. Of all the attacks described in this book, those against other users are evolving the most quickly, and they have been the focus of most research in recent years. Various recent trends in technology have somewhat altered the landscape of web applications. Popular consciousness about these trends exists by means of various rather misleading buzzwords, the most prominent of which are these. Web 2.0, this term refers to the greater use of functionality that enables user-generated content and information sharing, and also the adoption of various technologies that broadly support this functionality, including asynchronous HTTP requests and cross-domain integration. Chapter 1 Web Application in Security. 15. Cloud computing, this term refers to greater use of external service providers for various parts of the technology stack, including Applica, tie-on software, application platforms, web server software, databases, and hardware. It also refers to increased usage of virtualization technologies within hosting environments. As with most changes in technology, these trends have brought with them some new attacks and variations on existing attacks. Notwithstanding the hype, the issues raised are not quite as revolutionary as they may initially appear. We will examine the security implications of these and other recent trends in the appropriate locations throughout this book. Despite all the changes that have occurred within web applications, some categories of classic vulnerabilities show no sign of diminishing. They continue to arise in pretty much the same form as they did in the earliest days of the web. These include defects in business logic, failures to properly apply access controls, and other design issues. Even in a world of bolted-together Applica tie-on components and everything as a service, these timeless issues are likely to remain widespread. Summary. In a little over a decade, the World Wide Web has evolved from purely static information repositories into highly functional applications that process sensitive data and perform powerful actions with real-world consequences. During this development, several factors have combined to bring about the weak security posture demonstrated by the majority of today's web applications. Most applications face the core security problem that users can submit arbitrary input. Every aspect of the user's interaction with the application may be malicious and should be regarded as such unless proven otherwise. Failure to properly address this problem can leave applications vulnerable to attack in numerous ways. All the evidence about the current state of web application security indicates that although some aspects of security have indeed improved, entirely new threats have evolved to replace them. The overall problem has not been resolved. On any significant scale, attacks against web applications still present a serious threat to both the organizations that deploy them and the users who access them. Chapter 2. Core defense mechanisms. The fundamental security problem with web applications that all user input is untrusted, gives rise to a number of security mechanisms that applicants use to defend themselves against attack. Virtually all applications employ mechanisms that are conceptually similar, although the details of the design and the effectiveness of the implementation vary greatly. The defense mechanisms employed by web applications comprise the following core elements: handling user access to the application's data and functionality to prevent users from gaining unauthorized access, handling user input to the application's functions to prevent malformed input from causing undesirable behavior, handling attackers to ensure that the application behaves appropriately when being directly targeted, taking suitable defensive and offensive measures to frustrate the attacker, managing the application itself by enabling administrators to monitor its activities and configure its functionality. Because of their central role in addressing the core security problem, these mechanisms also make up the vast majority of a typical application's attack surface. If knowing your enemy is the first rule of warfare, then understanding 17 these mechanisms thoroughly is the main prerequisite for being able to attack. 18. Chapter 2: Core Defense Mechanisms. Applications effectively. If you are new to hacking web applications, and even if you are not, you should be sure to take time to understand how these core mechanisms work in each of the applications you encounter, and identify the weak points that leave them vulnerable to attack. Handling user access. A central security requirement that virtually any application needs to meet is controlling users' access to its data and functionality. A typical situation has several different categories of user, such as anonymous users, ordinary authenticate users, and administrative users. Furthermore, in many situations different users are permitted to access a different set of data. For example, users of a web mail application should be able to read their own email, but not other people's. Most web applications handle access using a trio of interrelated security mechanisms: authentication, session management, access control. Each of these mechanisms represents a significant area of an application's attack surface, and each is fundamental to an application's overall security posture. Because of their interdependencies, the overall security provided by the mechanisms is only as strong as the weakest link in the chain. A defect in any single component may enable an attacker to gain unrestricted access to the application's functionality and data. Authentication. The authentication mechanism is logically the most basic dependency in an application's handling of user access. Authenticating a user involves establishing that the user is in fact who he claims to be. Without this facility, the application would need to treat all users as anonymous, the lowest possible level of trust. The majority of today's web applications employ the conventional authentication model, in which the user submits a username and password, which the application checks for validity. Figure 2.1 shows a typical login function. In security-critical applications, such as those used by online banks, this basic model is usually supplemented by additional credentials and a multi-stage login process. When security requirements are higher still, other authentication modules may be used, based on client certificates, smart cards, or challenge response tokens. In addition to the core login process, authentication mechanisms often employ a range of other supporting functionality, such as self-registration, account recovery, and a password change facility. Chapter 2: Core Defense Mechanisms. 19. Figure 2.1, a typical login function. Despite their super-facile simplicity, authentication mechanisms suffer from a wide range of defects in both design and implementation. Common problems may enable an attacker to identify other users' usernames, guess their passwords, or bypass the login function by exploiting defects in its logic. When you are attacking a web application, you should invest a significant amount of attention to the various authentication-related functions it contains. Surprisingly, frequently, defects in this functionality enable you to gain unauthorized access to sensitive data and functionality. Session management. The next logical task in the process of handling user access is to manage the authenticated user session. After successfully logging into the application, the user accesses various pages and functions, making a series of HTTP requests from his browser. At the same time, the application receives countless other requests from different users, some of whom are authenticated and some of whom are anonymous. To enforce effective access control, the application needs a way to identify and process the series of requests that originate from each unique user. Virtually all web applications meet this requirement by creating a session for each user and issuing the user a token that identifies the session. The session itself is a set of data structures held on the server that track the state of the user's interaction with the application. The token is a unique string that the application maps to the session. When a user receives a token, the browser automatically submits it back to the server in each subsequent HTTP request, enabling the application to associate the request with that user. HTTP cookies are the standard method for transmitting session tokens, although many applications use hidden form files or the URL query string for this purpose. If a user does not make a request for a certain amount of time, the session is ideally expired, as shown in Figure 2.2. 20. Chapter 2: Core Defense Mechanisms. Figure 2.2, an application enforcing session timeout. In terms of attack surface, the session management mechanism is highly dependent on the security of its tokens. The majority of attacks against it seek to compromise the tokens issued to other users. If this is possible, an attacker can masquerade as the victim user and use the application just as if he had actually authenticated as that user. The principal areas of vulnerability arise from defects in how tokens are generated, enabling an attacker to guess the tokens issued to other users, and defects in how tokens are subsequently handled, enabling an attacker to capture other users' tokens. A small number of applications dispense with the need for session tokens by using other means of re-identifying users across multiple requests. If HTTP's built-in authentication mechanism is used, the browser automatically resubmits the user's credentials with each request, enabling the application to identify the user directly from these. In other cases, the application stores the state in format on the client side rather than the server, usually in encrypted form to prevent tampering. Access control. The final logical step in the process of handling user access is to make and enforce correct decisions about whether each individual request should be permitted or denied. If the mechanisms just described are functioning correctly, the applicator knows the identity of the user from whom each request is received. On this basis, it needs to decide whether that user is authorized to perform the action or access the data that he is requesting, as shown in Figure 2.3. The access control mechanism usually needs to implement some fine-grained logic, with different considerations being relevant to different areas of the application and different types of functionality. An application might support numerous user roles, each involving different combinations of specify C privileges. Individual users may be permitted to access a subset of the total data held within the application. Specify C functions may implement transaction limits and other checks, all of which need to be properly enforced based on the user's identity. Because of the complex nature of typical access control requirements, this mechanism is a frequent source of security vulnerabilities that enable an attacker. Chapter 2 Core Defense Mechanisms. 21. To gain unauthorized access to data and functionality, developers often make or assumptions about how users will interact with the application and frequently make oversights by omitting access control checks from some application functions. Probing for these vulnerabilities is often laborious because essentially the same checks need to be repeated for each item of functionality. Because of the prevalence of access control FLAWS, however, this effort is always a worthwhile investment when you are attacking a web application. Chapter 8 describes how you can automate some of the effort involved in performing rigorous access control testing. Figure 2.3, an application enforcing access control. Handling user input. Recall the fundamental security problem described in Chapter 1, all user input is untrusted. A huge variety of attacks against web applications involve submitting unexpected input, crafted to cause behavior that was not intended by the application's designers. Correspondingly, a key requirement for an application's security defenses is that the application must handle user input in a safe manner. Input-based vulnerabilities can arise anywhere within an application's functionality, and in relation to practically every type of technology in common use. Input validation is often cited as the necessary defense against these attacks. However, no single protective mechanism can be employed everywhere, and defending against malicious input is often not as straightforward as it sounds. Varieties of input. A typical web application processes user-supplied data in many different forms. Some kinds of input validation may not be feasible or desirable for all these forms of input. Figure 2.4 shows the kind of input validation often performed by a user registration function. 22. Chapter 2 Core Defense Mechanisms. Must contain at least 4 characters. Must contain at least 4 characters. Please provide a valid email address. Must contain only numbers. Figure 2.4, an application performing input validation. In many cases, an application may be able to impose very stringent validation checks on a specify C item of input. For example, a username submitted to a login function may be required to have a maximum length of 8 characters and contain only alphabetical characters. In other cases, the application must tolerate a wider range of possible input. For example, an address file ELD submitted to a personal details page might legitimately contain letters, numbers, spaces, hyphens, apostrophes, and other characters. However, for this item, restrictions still can be feasibly imposed. The data should not exceed a reasonable length limit, such as 50 characters, and should not contain any HTML markup. In some situations, an application may need to accept arbitrary input from users. For example, a user of a blogging application may create a blog whose subject is web application hacking. Posts and comments made to the blog may quite legitimately contain explicit attack strings that are being discussed. The application may need to store this input in a database, write it to disk, and display it back to users in a safe way. It cannot simply reject the input just because it looks potentially malicious without substantially diminishing the application's value to some of its user base. In addition to the various kinds of input that users enter using the browser interface, a typical application receives numerous items of data that began their life on the server and that are sent to the client so that the client can transmit them back to the server on subsequent requests. This includes items such as cookies and hidden form files, which are not seen by ordinary users of the application, but which an attacker can of course view and modify. In these cases, applications can often perform very specify C validation of the data received. For example, a parameter might be required to have one of a specify C set of known values, such as a cookie indicating the user's preferred language, or to be in a specify C format, such as a customer ID number. Furthermore, when an application detects that server-generated data has been modified in a way that is not possible for an ordinary user with a standard browser, this often indicates that the user is attempting to probe the application for vulnerabilities. In these. Chapter 2 Core Defense Mechanisms. 23. Cases, the application should reject the request and log the incident for potential investigation. See the Handling Attackers section later in this chapter. Approaches to input handling. Various broad approaches are commonly taken to the problem of handling user input. Different approaches are often preferable for different situations and different types of input, and a combination of approaches may sometimes be desirable. Reject known bad. This approach typically employs a blacklist containing a set of literal strings or patterns that are known to be used in attacks. The validation mechanism blocks any data that matches the blacklist and allows everything else. In general, this is regarded as the least effective approach to validating user input for two main reasons. First, a typical vulnerability in a web application. Tyon can be exploited using a wide variety of input, which may be encoded or represented in various ways. Except in the simplest of cases, it is likely that a blacklist will omit some patterns of input that can be used to attack the application. Tyon. Second, techniques for exploitation are constantly evolving. Novel methods for exploiting existing categories of vulnerabilities are unlikely to be blocked by current blacklists. Many blacklist-based file alters can be bypassed with almost embarrassing ease by making trivial adjustments to the input that is being blocked. For example, if select is blocked, try select. If or 1 equals 1 is blocked, try or 2 equals 2. If alert, XSS is blocked, try prompt, XSS. In other cases, file alters designed to block specify C keywords can be bypassed by using non-standard characters between expressions to disrupt the tokenizing performed by the application. For example, select an asterisk foo asterisk, a username, password, asterisk foo asterisk, from an asterisk foo asterisk, users, img%0910 equals alert, 1, src equals a. Finally, numerous blacklist-based file alters, particularly those implemented in web application fiery walls, have been vulnerable to null byte attacks. Because of the different ways in which strings are handled in managed and unmanaged execution contexts, inserting a null byte anywhere before a blocked expression can cause some file alters to stop processing the input and therefore not identify the expression. For example, %00, script alert, 1, script. 24. Chapter 2 Core Defense Mechanisms. Various other techniques for attacking web application fiery walls are described in Chapter 18. Note attacks that exploit the handling of null bytes arise in many areas of web application security. In contexts where a null byte acts as a string delimiter, it can be used to terminate a file name or a query to some backend component. In contexts where null bytes are tolerated and ignored, for example, within HTML in some browsers, arbitrary null bytes can be inserted within blocked expressions to defeat some blacklist-based file alters. Attacks of this kind are discussed in detail in later chapters. Except known good. This approach employs a whitelist containing a set of literal strings or patterns, or a set of criteria that is known to match only benign input. The validation mechanism allows data that matches the whitelist and blocks everything else. For example, before looking up a requested product code in the database, an application might validate that it contains only alphanumeric characters and is exactly 6 characters long, given the subsequent processing that will be done on the product code. The developers know that input passing this test cannot possibly cause any problems. In cases where this approach is feasible, it is regarded as the most effective way to handle potentially malicious input, provided that due care is taken in constructing the whitelist. An attacker will be unable to use crafted input to interfere with the application's behavior. However, in numerous situations, an application must accept data for processing that does not meet any reasonable criteria for what is known to be good. For example, some people's names contain an apostrophe or hyphen. These can be used in attacks against databases, but it may be a requirement that the application should permit anyone to register under his or her real name. Hence, although it is often extremely effective, the whitelist-based approach does not represent an all-purpose solution to the problem of handling user input. Sanitization. This approach recognizes the need to sometimes accept data that cannot be guaranteed as safe. Instead of rejecting this input, the application sanitizes it in various ways to prevent it from having any adverse effects. Potentially malicious characters may be removed from the data, leaving only what is known to be safe, or they may be suitably encoded or escaped before further processing is performed. Approaches based on data sanitization are often highly effective, and in many situations they can be relied on as a general solution to the problem of malicious. Chapter 2 Core Defense Mechanisms. 25. Input. For example, the usual defense against cross-site scripting attacks is to HTML encode dangerous characters before these are embedded into pages of the application. See Chapter 12. However, effective sanitization may be difficult to achieve if several kinds of potentially malicious data need to be accommodated within one item of input. In this situation, a boundary validation approach is desirable, as described later. Safe data handling. Many web application vulnerabilities arise because user-supplied data is processed in unsafe ways. Vulnerabilities often can be avoided not by validating the input itself, but by ensuring that the processing that is performed on it is inherently safe. In some situations, safe programming methods are available that avoid common problems. For example, SQL injection attacks can be prevented through the correct use of parameterized queries for database access. See Chapter 9. In other situations, application functionality can be designed in such a way that inherently unsafe practices, such as passing user input to an operating system command interpreter, are avoided. This approach cannot be applied to every kind of task that web applications need to perform. But where it is available, it is an effective general approach to handling potentially malicious input. Semantic checks. The defenses described so far all address the need to defend the application against various kinds of malformed data whose content has been crafted to interfere with the application's processing. However, with some vulnerabilities, the input supplied by the attacker is identical to the input that an ordinary, non-malicious user may submit. What makes it malicious is the different circumstances under which it is submitted. For example, an attacker might seek to gain access to another user's bank account by changing an account number transmitted in a hidden form FI ELD. No amount of syntactic validation will distinguish between the user's data and the attacker's. To prevent unauthorized access, the applicator needs to validate that the account number submitted belongs to the user who has submitted it. Boundary validation. The idea of validating data across trust boundaries is a familiar one. The core security problem with web applications arises because data received from users is untrusted. Although input validation checks implemented on the client side may improve performance and the user's experience, they do not provide any assurance about the data that actually reaches the server. The point at which 26. Chapter 2 Core Defense Mechanisms. User data is FI RST received by the server-side application represents a huge trust boundary. At this point, the application needs to take measures to defend itself against malicious input. Given the nature of the core problem, it is tempting to think of the input validation problem in terms of a frontier between the internet, which is bad and untrusted, and the server-side application, which is good and trusted. In this picture, the role of input validation is to clean potentially malicious data on arrival and then pass the clean data to the trusted application. From this point onward, the data may be trusted and processed without any further checks or concern about possible attacks. As will become evident when we begin to examine some actual vulnerabilities, this simple picture of input validation is inadequate for several reasons. Given the wide range of functionality that applications implement and the different technologies in use, a typical application needs to defend itself against a huge variety of input-based attacks, each of which may employ a diverse set of crafted data. It would be very difficult to devise a single mechanism at the external boundary to defend against all these attacks. Many application functions involve chaining together a series of different types of processing. A single piece of user-supplied input might result in a number of operations in different components, with the output of each being used as the input for the next. As the data is transformed, it might come to bear no resemblance to the original input. A skilled attacker may be able to manipulate the application to cause malicious input to be generated at a key stage of the processing, attacking the component that receives this data. It would be extremely difficult to implement a validator tie-on mechanism at the external boundary to foresee all the possible results of processing each piece of user input. Defending against different categories of input-based attack may entail performing different validation checks on user input that are incompatible with one another. For example, preventing cross-site scripting attacks may require the application to HTML encode the character as in GT, and preventing command injection attacks may require the application to block input containing the and characters. Attempting to prevent all categories of attack simultaneously at the application's external boundary may sometimes be impossible. A more effective model uses the concept of boundary validation. Here, each individual component or functional unit of the server-side application treats its inputs as coming from a potentially malicious source. Data validation is performed at each of these trust boundaries, in addition to the external frontier between the client and server. This model provides a solution to the problems just described. Each component can defend itself against the specified C types of crafted input to which it may be vulnerable as data passes through different. Chapter 2 Core Defense Mechanisms. 27. Components, validation checks can be performed against whatever value the data has as a result of previous transformations. And because the various validation checks are implemented at different stages of processing, they are unlikely to come into conflict ICT with one another. Figure 2.5 illustrates a typical situation where boundary validation is the most effective approach to defending against malicious input. The user login results in several steps of processing being performed on user-supplied input, and suitable validation is performed at each step. 1. The application receives the user's login details. The form handler Waal dates that each item of input contains only permitted characters, is within a specified C length limit, and does not contain any known attack signatures. 2. The application performs a SQL query to verify the user's credentials. To prevent SQL injection attacks, any characters within the user input that may be used to attack the database are escaped before the query is constructed. 3. If the login succeeds, the application passes certain data from the user's profiler to a SOAP service to retrieve further information about her account. To prevent SOAP injection attacks, any XML metacharacters within the user's profiler data are suitably encoded. 4. The application displays the user's account information back to the user's browser. To prevent cross-site scripting attacks, the application HTML encodes any user-supplied data that is embedded into the returned page. 2. Clean SQL. 1. General checks. User login submission. Display account details. 4. Sanitize output. SQL query. Application server. SOAP message. Database. 3. Encode XML metacharacters. SOAP service. Figure 2.5. An application function using boundary validation at multiple stages of processing. 28. Chapter 2 Core Defense Mechanisms. The specify C vulnerabilities and defenses involved in this scenario will be examined in detail in later chapters. If variations on this functionality involved passing data to further application components, similar defenses would need to be implemented at the relevant trust boundaries. For example, if a failed login caused the application to send a warning email to the user, any user data incorporated into the email may need to be checked for SMTP injection attacks. Multi-step validation and canonicalization. A common problem encountered by input handling mechanisms arises when user-supplied input is manipulated across several steps as part of the validator tie-on logic. If this process is not handled carefully, an attacker may be able to construct crafted input that succeeds in smuggling malicious data through the validation mechanism. One version of this problem occurs when an application attempts to sanitize user input by removing or encoding certain characters or expressions. For example, an application may attempt to defend against some cross-site scripting attacks by stripping the expression script from any user-supplied data. However, an attacker may be able to bypass the filter by supplying the following input. SCR script ipt. When the blocked expression is removed, the surrounding data contracts to restore the malicious payload because the filter is not being applied recursively. Similarly, if more than one validation step is performed on user input, an attacker may be able to exploit the ordering of these steps to bypass the filter. For example, if the application FIRST removes recursively and then removes /recursively, the following input can be used to defeat the validation. /o. A related problem arises in relation to data canonicalization. When input is sent from the user's browser, it may be encoded in various ways. These encoding schemes exist so that unusual characters and binary data may be transmitted safely over HTTP. See Chapter 3 for more details. Canonicalization is the process of converting or decoding data into a common character set. If any canonicalization is carried out after input filters have been applied, an attacker may be able to use a suitable encoding scheme to bypass the validation mechanism. For example, an application may attempt to defend against some SQL inject tie-on attacks by blocking input containing the apostrophe character. However, if Chapter 2 Core Defense Mechanisms 29. The input is subsequently canonicalized, an attacker may be able to use double URL encoding to defeat the filter. For example, %2527. When this input is received, the application server performs its normal URL decode, so the input becomes %27. This does not contain an apostrophe, so it is permitted by the application's filters. But when the application performs a further URL decode, the input is converted into an apostrophe, thereby bypassing the filter. If the application strips the apostrophe instead of blocking it, and then performs further canonicalization, the following bypass may be effective. %2727. It is worth noting that the multiple validation and canonicalization steps in these cases need not all take place on the server side of the application. For example, in the following input several characters have been HTML encoded. If frame src equals j, and #x61, vasc, and #x72 ipt, and #x3a, alert, and #x28, 1, and #x29. If the server-side application uses an input filter to block certain JavaScript expressions and characters, the encoded input may succeed in bypassing the filter. However, if the input is then copied into the application's response, some browsers perform an HTML decode of the src parameter value, and the embedded JavaScript executes. In addition to the standard encoding schemes that are intended for use in web applications, canonicalization issues can arise in other situations where a component employed by the application converts data from one character set to another. For example, some technologies perform a best phi-t mapping of characters based on similarities in their printed glyphs. Here, the characters and may be converted into and respectively, and y and a are converted into y and a. This behavior can often be leveraged to smuggle blocked characters or keywords past an application's input filters. Throughout this book, we will describe numerous attacks of this kind, which are effective in defeating many applications' defenses against common input-based vulnerabilities. Avoiding problems with multi-step validation and canonicalization can sometimes be difficult, and there is no single solution to the problem. One approach is to perform sanitization steps recursively, continuing until no further modify cations have been made on an item of input. However, where the desired sanitization involves escaping a problematic character, this may result in an infinite loop. Often, the problem can be addressed only on a case-by-case basis, based on the types of validation being performed. Where feasible, it may be preferable to avoid attempting to clean some kinds of bad input, and simply reject it altogether. 30. Chapter 2 Core Defense Mechanisms. Handling attackers. Anyone designing an application for which security is remotely important must assume that it will be directly targeted by dedicated and skilled attackers. A key function of the application's security mechanisms is being able to handle and react to these attacks in a controlled way. These mechanisms often incorporate a mix of defensive and offensive measures designed to frustrate an attacker as much as possible and give the application's owners appropriate notification and evidence of what has taken place. Measures implemented to handle attackers typically include the following tasks: handling errors, maintaining audit logs, alerting administrators, reacting to attacks, handling errors. However careful an application's developers are when validating user input, it is virtually inevitable that some unanticipated errors will occur. Errors resulting from the actions of ordinary users are likely to be identified during functional IT and user acceptance testing. Therefore, they are taken into account before the application is deployed in a production context. However, it is difficult to anticipate every possible way in which a malicious user may interact with the application, so further errors should be expected when the application comes under attack. A key defense mechanism is for the application to handle unexpected errors gracefully, and either recover from them or present a suitable error message to the user. In a production context, the application should never return any system-generated messages or other debug information in its responses. As you will see throughout this book, overly verbose error messages can greatly assist malicious users in furthering their attacks against the application. In some situations, an attacker can leverage defective error handling to retrieve sensitive type information within the error messages themselves, providing a valuable channel for stealing data from the application. Figure 2.6 shows an example of an unhandled error resulting in a verbose error message. Most web development languages provide good error handling support. Through try-catch blocks and checked exceptions, application code should make extensive use of these constructs to catch specify C and general errors and handle them appropriately. Furthermore, most application servers can be configured to deal with unhandled application errors in customized ways, such as Chapter 2 Core Defense Mechanisms. 31. By presenting an uninformative error message. See Chapter 15 for more details on these measures. Figure 2.6, an unhandled error. Effective error handling is often integrated with the application's logging mechanisms, which record as much debug information as possible about anticipated errors. Unexpected errors often point to defects within the application's defenses that can be addressed at the source if the application's owner has the required information. Maintaining audit logs. Audit logs are valuable primarily when investigating intrusion attempts against an application. Following such an incident, effective audit logs should enable the application's owners to understand exactly what has taken place, which vulnerabilities, if any, were exploited, whether the attacker gained unauthorized access to data or performed any unauthorized actions, and as far as possible, provide evidence of the intruder's identity. 32. Chapter 2 Core Defense Mechanisms. In any application for which security is important, key events should be logged. As a matter of course. At a minimum, these typically include the following. All events relating to the authentication functionality, such as successful and failed login and change of password. Key transactions, such as credit card payments and funds transfers. Access attempts that are blocked by the access control mechanisms. Any requests containing known attack strings that indicate overtly malicious intentions. In many security-critical applications, such as those used by online banks, every client request is logged in full, providing a complete forensic record that can be used to investigate any incidents. Effective audit logs typically record the time of each event, the IP address from which the request was received, and the user's account, if authenticated. Such logs need to be strongly protected against unauthorized read or write access. An effective approach is to store audit logs on an autonomous system that accepts only update messages from the main application. In some tie-ins, logs may be FLUShed to write-once media to ensure their integrity in the event of a successful attack. In terms of attack surface, poorly protected audit logs can provide a gold mine of information to an attacker, disclosing a host of sensitive information such as session tokens and request parameters. This information may enable the attacker to immediately compromise the entire application, as shown in Figure 2.7. Figure 2.7, poorly protected application logs containing sensitive information submitted by other users. Chapter 2 Core Defense Mechanisms. 33. Alerting administrators. Audit logs enable an application's owners to retrospectively investigate intrusion attempts and, if possible, take legal action against the perpetrator. However, in many situations it is desirable to take much more immediate action, in real time, in response to attempted attacks. For example, administrators may block the IP address or user account an attacker is using. In extreme cases, they may even take the application offline while investigating the attack and taking remedial action. Even if a successful intrusion has already occurred, its practical effects may be mitigated if defensive action is taken at an early stage. In most situations, alerting mechanisms must balance the conflicting objectives of reporting each genuine attack reliably and of not generating so many alerts that these come to be ignored. A well-designed alerting mechanism can use a combination of factors to diagnose that a determined attack is underway and can aggregate related events into a single alert where possible. Anomalous events monitored by alerting mechanisms often include the following. Usage anomalies, such as large numbers of requests being received from a single IP address or user, indicating a scripted attack. Business anomalies, such as an unusual number of funds transfers being made to or from a single bank account. Requests containing known attack strings. Requests where data that is hidden from ordinary users has been modified. Some of these functions can be provided reasonably well by off-the-shelf application fiery walls and intrusion detection products. These typically use a mixture of signature and anomaly-based rules to identify malicious use of the application and may reactively block malicious requests as well as issue alerts to administrators. These products can form a valuable layer of defense, protecting a web application, particularly in the case of existing applications known to contain problems, but where resources to fix these are not immediately available. However, their effectiveness usually is limited by the fact that each web application is different, so the rules employed are inevitably generic. To some extent, web application fiery walls usually are good at identifying the most obvious attacks, where an attacker submits standard attack strings in each request parameter. However, many attacks are more subtle than this. For example, perhaps they modify the account number in a hidden file ELD to access another user's data, or submit requests out of sequence to exploit defects in the application's logic. In these cases, a request submitted by an attacker may be 34. Chapter 2 Core Defense Mechanisms. Identical to that submitted by a benign user. What makes it malicious are the circumstances under which it is made. In any security-critical application, the most effective way to implement real-time alerting is to integrate this tightly with the application's input validation mechanisms and other controls. For example, if a cookie is expected to have one of a specified set of values, any violation of this indicates that its value has been modified in a way that is not possible for ordinary users of the application. Similarly, if a user changes an account number in a hidden file ELD to identify a different user's account, this strongly indicates malicious intent. The application should already be checking for these attacks as part of its primary defenses. And these protective mechanisms can easily hook into the application's alerting mechanism to provide fully customized indicators of malicious activity. Because these checks have been tailored to the application's actual logic with a fine and ingrained knowledge of how ordinary users should be behaving, they are much less prone to false positives than any off-the-shelf solution, however configurable or easy to learn that solution may be. Reacting to attacks. In addition to alerting administrators, many security-critical applications time built-in mechanisms to react defensively to users who are identified as potentially malicious. Because each application is different, most real-world attacks require an attacker to probe systematically for vulnerabilities, submitting numerous requests containing crafted input designed to indicate the presence of various common vulnerabilities. Effective input validation mechanisms will identify many of these requests as potentially malicious and block the input from having any undesirable effect on the application. However, it is sensible to assume that some bypasses to these file filters exist, and that the application does contain some actual vulnerabilities waiting to be discovered and exploited. At some point, an attacker working systematically is likely to discover these defects. For this reason, some applications take automatic reactive measures to frustrate the activities of an attacker who is working in this way. For example, they might respond increasingly slowly to the attacker's requests or terminate the attacker session, requiring him to log in or perform other steps before continuing the attack. Although these measures will not defeat the most patient and determined attacker, they will deter many more casual attackers, and will buy additional time for administrators to monitor the situation and take more drastic action if desired. Chapter 2 Core Defense Mechanisms. 35. Reacting to apparent attackers is not, of course, a substitute for fighting any vulnerabilities that exist within the application. However, in the real world, even the most diligent efforts to purge an application of security FLAWS may leave some exploitable defects. Placing further obstacles in the way of an attacker is an effective defense in-depth measure that reduces the likelihood that any residual vulnerabilities will be found and exploited. Managing the application. Any useful application needs to be managed and administered. This facility often forms a key part of the application's security mechanisms, providing a way for administrators to manage user accounts and roles, access monitoring, and audit functions, perform diagnostic tasks, and configure aspects of the application's functionality. In many applications, administrative functions are implemented within the application itself, accessible through the same web interface as its core non-security functionality, as shown in Figure 2.8. Where this is the case, the administrative mechanism represents a critical part of the application's attack surface. Its primary attraction for an attacker is as a vehicle for privilege escalation. For example, weaknesses in the authentication mechanism may enable an attacker to gain administrative access, effectively compromising the entire application. Many applications do not implement effective access control of some of their administrative functions. An attacker may find a means of creating a new user account with powerful privileges. Administrative functionality often involves displaying data that originated from ordinary users. Any cross-site scripting FLAWS within the administrative interface can lead to compromise of a user session that is guaranteed to have powerful privileges. Administrative functionality is often subjected to less rigorous security testing because its users are deemed to be trusted, or because penetration testers are given access to only low-privileged accounts. Furthermore, the functionality often needs to perform inherently dangerous operations involving access to files on disk or operating system commands. If an attacker can compromise the administrative function, he can often leverage it to take control of the entire server. 36. Chapter 2 Core Defense Mechanisms. Figure 2.8, an administrative interface within a web application. Summary. Despite their extensive differences, virtually all web applications employ the same core security mechanisms in some shape or form. These mechanisms represent an application's primary defenses against malicious users and therefore also comprise the bulk of the application's attack surface. The vulnerabilities we will examine later in this book mainly arise from defects within these core mechanisms. Of these components, the mechanisms for handling user access and user input are the most important and should receive most of your attention when you are targeting an application. Defects in these mechanisms often lead to complete compromise of the application, enabling you to access data belonging to other users, perform unauthorized actions, and inject arbitrary code and commands. Questions. Answers can be found at //mdcec.net or 1. Why are an application's mechanisms for handling user access only as strong as the weakest of these components? 2. What is the difference between a session and a session token? 3. Why is it not always possible to use a whitelist-based approach to input validation? Chapter 2 Core Defense Mechanisms. 37. 4. You are attacking an application that implements an administrative func. Tie-on. You do not have any valid credentials to use the function. Why should you nevertheless pay close attention to it? 5. An input validation mechanism designed to block cross-site scripting. Attacks performs the following sequence of steps on an item of input. 1. Strip any script expressions that appear. 2. Truncate the input to 50 characters. 3. Remove any quotation marks within the input. 4. URL decode the input. 5. If any items were deleted, return to step 1. Can you bypass this validation mechanism to smuggle the following data past it? Script alert foo script. Chapter 3. Web application technologies. Web applications employ a myriad of technologies to implement their function. Aliti. This chapter is a short primer on the key technologies that you are likely to encounter when attacking web applications. We will examine the HTTP protocol, the technologies commonly employed on the server and client sides, and the encoding schemes used to represent data in different situations. These technologies are in general easy to understand, and a grasp of their relevant features is key to performing effective attacks against web applications. If you are already familiar with the key technologies used in web applications, you can skim through this chapter to confirm that it offers you nothing new. If you are still learning how web applications work, you should read this chapter before continuing to the later chapters on specify C vulnerabilities. For further reading on many of the areas covered, we recommend HTTP, the definitive guide by David Gawley and Brian Totti, O'Reilly, 2002, and also the website of the World Wide Web Consortium at www.w3.org. The HTTP protocol. Hypertext Transfer Protocol, HTTP, is the core communications protocol used to access the World Wide Web and is used by all of today's web applications. It is a simple protocol that was originally developed for retrieving static text-based resources. It has since been extended and leveraged in various ways to enable it to support the complex distributed applications that are now commonplace. 39. 40. Chapter 3 Web Application Technologies. HTTP uses a message-based model in which a client sends a request message and the server returns a response message. The protocol is essentially connectionless. Although HTTP uses the stateful TCP protocol as its transport mechanism, each exchange of request and response is an autonomous transaction and may use a different TCP connection. HTTP requests. All HTTP messages, requests and responses consist of one or more headers, each on a separate line, followed by a mandatory blank line, followed by an optional message body. A typical HTTP request is as follows. Get auth a 488, your details.hash, UD equals 129 HTTP, 1.1 accept, application, XMS application, image of JPEG, application, XAML plus XML, image of GIF, image of PJPEG, application, XMS XBAP, application, Shockwave flash, asterisk refer, HTTPS, // mdcac.net author, 488, home.ash accept language, ENGB user agent, Mozilla a 4.0, compatible, MSIE 8.0, Windows NT 6.1, Waal 64, Trident 4.0, SLCC 2. .NET CLR 2.0.50727, .NET CLR 3.5.30729, .NET CLR 3.0.30729, .NET 4.0C, Infopath.3, .NET 4.0E, FDM, .NET CLR the 1st of January 4322, accept encoding, zip. Deflate host, MDCEC.NET connection, keep alive cookie, session ID equals 5B70C71F3FD4968935CDB6682E545476. The phi-RST line of every HTTP request consists of 3 items, separated by spaces. A verb indicating the HTTP method. The most commonly used method is get, whose function is to retrieve a resource from the web server. Get requests do not have a message body, so no further data follows the blank line after the message headers. The requested URL. The URL typically functions as a name for the resource being requested, together with an optional query string containing param etas that the client is passing to that resource. The query string is indicated by the character in the URL. The example contains a single parameter with the name UD and the value 129. The HTTP version being used. The only HTTP versions in common use on the internet are 1.0 and 1.1, and most browsers use version 1.1 by default. There are a few differences between the specified cations of these 2 versions. However, the only difference you are likely to encounter when attacking web applications is that in version 1.1 the host request header is mandatory. Chapter 3 Web Application Technologies. 41. Here are some other points of interest in the sample request. The refer header is used to indicate the URL from which the request originated, for example, because the user clicked a link on that page. Note that this header was misspelled in the original HTTP specified cation, and the misspelled version has been retained ever since. The user agent header is used to provide information about the browser or other client software that generated the request. Note that most browsers include the Mozilla Prefix X for historical reasons. This was the user agent string used by the originally dominant Netscape browser, and other browsers wanted to assert to websites that they were compatible with this standard. As with many quirks from computing history, it has become so established that it is still retained, even on the current version of Internet Explorer, which made the request shown in the example. The host header specify as the host name that appeared in the full URL being accessed. This is necessary when multiple websites are hosted on the same server, because the URL sent in the phi-RST line of the request usually does not contain a host name. See Chapter 17 for more information about virtually hosted websites. The cookie header is used to submit additional parameters that the server has issued to the client, described in more detail later in this chapter. HTTP responses. A typical HTTP response is as follows. HTTP 1.1200 OK date, Tuesday, the 19th of April 2011 9:23 and 32 seconds Greenwich Mean Time server, Microsoft iOS, the 6.0x powered by ASP.NET set cookie, tracking equal